Well, first of all, I would like to present a message from Pedro, who wasn't able to make it here. He thanks you for the invitation, but he had an important meeting with the president of Abengoa right now actually in Madrid. And he said that maybe he will be here later, but we'll see if he makes it. So coming back to me, my name is Cosmin Koșciu-Botaru. I'm from Abengoa Research, and I will present to you today some ideas about the impacts of microgrids on the power network. During this presentation, I will express some ideas about the integration of distributed energy resources into the power system. I will present some technological areas that are driving the implementation of smart grid. I will then get to effects of microgrids on the power system, discuss some issues about communications in smart grids, and then focus on protection and system reconfiguration or self-healing in the smart grid. I will conclude with some future expectations about the smart grid. I didn't prepare any slides for Abengoa, but I can tell you that the main business of Abengoa is in the upper layers of the power system, where you have the transmission and sub-transmission. And so far, the business ends here at the distribution level. It doesn't go below. So it's usually installing large transmission lines, big power plants, big quantities of energy and power transported over the transmission lines. Our power network today is undertaking major changes, transforming from a single direction power flow, as it was designed when implemented almost 100 years ago, is changing to a multiple or bidirectional power flow due to the integration of distributed energy resources in different levels of the power grid. Until recently, the energy was produced in large concentrated power plants and was transmitted through the power system over large distances until it reached the end consumer or the industry. Nowadays, this is changing, and distributed energy resources are entering the power system from the sub-transmission level downwards. For example, to give an idea about the size of these power plants, in the sub-transmission grid, we have distributed generation plants in the range or even exceeding 100 megawatts. In the distribution grid, where the most industry is located and also large population areas are fed with power, the DG plants are in the level of 10 to 100 megawatts. And getting to the consumption level, the last level of the power grid, where we have the low voltage consumer, usually the DG installations are in the range of a few kilowatts to 1 megawatt. What is a microgrid? A very concise definition of a microgrid would be a localized grouping of distributed generation units, storage, and loads. These energy generation units can be photovoltaic panels, could be small wind turbines, diesel generators, micro hydro, micro gas, micro CHPs. Some characteristics of these generation units are the size, which are much smaller compared to the centralized power plants, and they are also located in the close proximity of the user, thus minimizing the losses due to transmission. The major characteristic of the microgrid is the point of common coupling, the point where the microgrid is connected to the power system, and the fact that it can run both in a connected and disconnected mode. Seen from the power system side, the microgrid can look like a load or a generator, depending on the power management. Rather, if the consumption is lower than the generation, then we have a load. Or if the generation is larger than the load at the microgrid level, then we can see it as a generator. The benefits of microgrids. To name a few, microgrids are playing an essential solution for isolated communities, which are geographically far away from the main grid. Also, they provide a solution for critical loads as hospitals, data centers, or military applications. They have the benefit that usually they use green energy and are environmentally friendly, reducing the CO2 emissions. And they can manage this locally produced energy in a more efficient way. The technological areas responsible for the large development of smart grids would be these four. So we have the power electronics, which are responsible for designing and developing electronic devices that are producing, converting, and transporting energy from different sources. We have the control system theory, which is used to design algorithms to control such complex systems. We have the information technology, or the IT, which is responsible for developing this control algorithm and implement them on the device. And so we also have this term coined, the intelligent electronic device, the IED, which is in fact an electronic device with some different functions or services. Another pillar for this microgrid development are the communications, which are essential for information exchange between the IEDs and to provide reliable information to the control systems. We can see the impact of microgrids on the power system through two perspectives. First would be the electric power exchange, and the second would be the information exchange. As I said before, at the point of common coupling, the microgrids have to be able to provide services to the power grid, like voltage regulation, contingency, power reserve, thus improving the power quality and reliability. For the information exchange point of view, the IDs in the microgrid must be able to transmit status information, measurements, and signals, both between the devices in the microgrid and also to the upper hierarchical control layers, like the distribution network operator, which is managing the distribution network, and even higher to the transmission system operator that is responsible for stabilizing and supplying large areas of the power system. As I said, and now I will focus a bit on the communication in smart grids. The communications are essential, and during the years, multiple protocols have been developed, both for vendor-specific and standard protocols, like the DNP3 and Profibus. In the last years, a new protocol is very promising, the IEC-61850, and I want to tell you just some words about this. Its main characteristic is the object-oriented approach in definition of the data. Another important characteristic is the separation between the data representation and the configuration of the communication. Thus, this protocol is able to be translated for future communication networks. The protocol defines 3 messages, each designed to transmit specific data. For instance, the backbone of this protocol is the MMS message, which is used for SCADA functions like setting references and reading values. It uses a server-client communication type, linking to 2 IDs through IP addressing. The second would be the Goose message, which is used to send critical time information between IDs. To achieve this very small amount of time in transmission, it uses a multicast communication between a publisher and a subscriber, and uses the MAC addressing without any packet confirmation received message. And the third one, because I said there is a third one, is the SV, also called the sampled values, which uses the same procedure with the publisher and subscriber, like the Goose, and is used to stream data containing measurements from current and voltage transducers. This is used instead of hard wires. The smart grid can be said that has 2 levels of intelligence. To manage the energy process, which was discussed so far, with the low demand, with the shading, with synchronization, so on. And the second one would be to manage the fault conditions and reconfigure or self-heal the grid. The main task of a protection algorithm is that when a fault occurs, which can be an overcurrent or an overvoltage, the faulty section of the system is isolated from the healthy one due to the reconfiguration of the grid and changing the status of different breakers and switches. This reconfiguration is quite a challenging task in the new smart grid because of the distributed energy resources penetration, and the fact that the power flow can change the direction, and especially in a microgrid where we can have different aspects of the protection when operating in an isolated or connected mode. After the fault occurs, the breaker that senses the overcurrent or the fault opens, leaving an area of the power system de-energized. Then a second algorithm must run, which is to try to reconnect as many subsections of the faulty section as possible by reconfiguring the network and opening the switches. This reconfiguration can be realized in a centralized or decentralized manner. Both of these are can use the IC protocol very well with the designated messages. In both ways, breakers and switches must be equipped with intelligence, that is, with controllers that can run algorithms for fault location isolation and system service restoration, system reconfiguration, and self-heal. For the second part, the second algorithm, the system reconfiguration, we have some performance indicators which were heard in the first presentation, so I won't get into details. I would say that this reconfiguration is a NP complete problem. That means that we cannot know the general optimal solution until we evaluated all the possible solutions. This can be time-consuming and requires an intense power computation, and it can be done only at a centralized level. However, we can be satisfied with the first solution that reaches a local optimum. And in this case, we can have a distributed reconfiguration algorithm. For instance, here we have a power system, and the first section, the upper section, is fed through this transformer on the right, and we have the bottom section, which is fed with power through the transformer on the left. A fault occurs. This breaker senses the fault, and it will interrupt power flowing through this side, and these loads will be de-energized. When the fault location isolation and reconfiguration algorithm is being run, it has to take into account the constraints of the system. That is, the current limitations on the feeder, and also the power limitations of the transformer. We cannot run infinite amount of power through the feeder or request as much from the transformer. So after the algorithm is running, we see that there was a shift in the source of power for this section. This is now fed from the left, and the lower part of the grid is now fed with power through the right. A short comparison between the two ways of seeing this algorithm. Very short, in the distributed photo location algorithm. We implement one algorithm on each breaker and feeder, and they will reconfigure the grid online, exchanging messages, especially goose messages from the IEC, and the centralized algorithm reads data from the entire system, runs a complex algorithm, and can reach that global optimum that I was telling you about in the beginning. Having a centralized algorithm, we can also send references to non-critical loads or shading loads to try to get to this optimum reconfiguration. As future expectations for the smart grid from the power system, from the transmission level, would be the jointly control or aggregation of many microgrids to optimize the interaction with the main grid. This is related to virtual power plants that was talked about earlier. We have to, and the basic idea is there will always be the need of the transmission grid to move large amount of power to give the microgrids the reliability and to ensure the operation of each loads regarding the operation of the distribution energy resources. And before I end, this I found a very interesting resource for the young researchers in the smart grid. This is a smart grid standard map. You have the link here. So it presents the entire grid, starting with generation, transmission, distribution, distributed energy resources, consumption, and different levels. You have here the operation, the enterprise, the market, and you can select different standards, standard protocols. I selected the IEC 61850, and you can see each standard where does it have impact. And as you see, this standard is pretty much everywhere, except the consumption. Okay, so thank you very much.